I want to kind of deviate from the more detailed stuff that people have been presenting, even the ones that people have said are kind of notional, we're kind of just at the ground floor of developing these, are a little more advanced than what I'm going to talk about here, because what I want to look at is more of a paradigm level shift in the way we can do planetary science exploration, making use of a Cubesat type probe. And this is something that we've been developing sort of a joint partnership with some industrial partners in genetics, students at the University of Arizona and the College of Engineering and the Spacecraft Consortium, and then scientifically with my co-authors. The idea here is to do a sort of large-scale exploration of small bodies in the inner solar system, and to sort of present a scientific rationale for why you want to do this on a large scale. I'm going to just sort of talk about the various ways in which small bodies are important to us scientifically and also to us both in terms of civilization and as a resource. So those of us who study small bodies, and you've heard this now multiple times, which sort of leads to this whole idea that small bodies are a good spot for using this type of spacecraft. Asteroids are one of the two sort of broad classes of planetesimals. Both of them have sort of the same basic relevance. In the case of asteroids, we think of those as sort of the bricks and mortars of the terrestrial planets, Mercury, Mars, Venus, and Earth. And there are a huge number of them that are still in the solar system, ranging in size from tens of meters down to meters, all the way up to protoplanets. And they have a tremendous amount of compositional diversity. And that compositional diversity reflects a variety of processes and also may reflect the compositional characteristics that make up the terrestrial planets that we think these are the bricks and mortars of. And they have a modern dynamical organization that tells us a lot about early migration processes and ongoing gravitational perturbations in the solar system. Comets are the second class. They're basically outer solar system asteroids. They formed in a region where they were cold enough that you could condense out ices directly onto interstellar grains. As a result, they have a much higher volatile content. There's still a lot of dust inside them, but they also have water and other organics. Basically, their composition, their isotopic composition, the molecular compounds that we find inside them are really telling us what the temperature, composition, density, and mixing processes were in the protoplanetary disk during the period when planetesimals were formed. They have modern reservoirs in the Kuiper belt and in the Oort cloud, which are stable and unstable resonances in the inner solar system in the form of centaurs, Jupiter family, and other periodic comets. That's telling us about late-stage planetary migration and also about the rate at which there are non-contacting interactions ongoing in the solar system today. And there's an ongoing question about how much cometary impacts contributed to the volatile budgets of the terrestrial planets. That's something that we're still exploring. Now, on a more pragmatic level, these objects mean something to us because they could also be a potential threat. We're not currently looking at an Armageddon-like scenario where a Texas-sized asteroid is going to wipe out the planet and we need Bruce Willis to fly there and destroy it. But we do have impacts ongoing, and in fact, within the last 100 years, we have had an impact with an object in the neighborhood of 60 to 100 meters in diameter. That if it were to happen today, if we were to have a Tunguska today over a major city, it would have a question if we wipe it out. So we need to understand how to identify these objects all the way down to fairly small ones. We need to understand how their orbits evolve, non-gravitationally as well as gravitationally. And we need to understand how to mitigate the threat once we identify something that might hit us in 200 or 300 years. We know very little about how to do those things. All right, well, the one that went by, and I can't seem to get back to, is also the idea, this emerging idea that we can use these as resources for volatiles, to grow food, to make fuel, to build spacecraft, to do all kinds of things. Some of this material can be delivered to Earth for economic benefits. A lot of it can be used in space to build space infrastructure. Because it costs so much to get things into space, that means that there's potentially trillions of dollars in economic value if we can begin to mine these out. The problem is that our history of exploration of small bodies hasn't led us to a point where we can really answer any of the major questions that we have right now. Historically, this is our model for working with small bodies up until about 30 years ago. All we had was ground-based remote sensing. These objects were unresolved, so all we could do was look at their bulk reflectance, measure the gases that were coming off and how they evolved. It was a relatively limited approach for understanding them. Better. And we could come up with classifications, and we did. So we have, chondritic asteroids, metallic asteroids, visitations asteroids, asteroid families, comets, comets that are carbon depleted, comets that aren't carbon depleted, all manner of things. But all we could do from looking at them was to assume that they had consistent bulk properties that didn't show any particular variability other than that it was reflected in a certain way. So trying to understand internal composition, we couldn't do that. We could have a limited understanding of rotational characteristics, but often the results were degenerate with multiple possibles. Unless an object came within about 1/10 of an AU, it was really not even possible to do something like radar mapping of surface features. So we knew very little about these objects as actual physical things. So starting around the mid-1980s, we began what I like to call the weaning off model. We started going to these objects and started sampling them directly, treating them as individual bodies for exploration. And by and large, a lot of these are very, very capable missions. So I'm putting up some examples from various space agencies, some that are soon happened, some that are ongoing, some that are finished. Rosetta's just completed its mission. My institution is the PI institution for the OSIRIS-REx mission. It's going to Bennu, so we take a direct sample and bring it back. There's the Hayabusa mission, Hayabusa 2 mission that's going to also do sample testing and actually try to fire a explosive projectile into an asteroid. That should be very interesting. These experiments can do a lot. They can do spectroscopy, mass spectroscopy, detailed imaging, hyperspectral imaging, all kinds of things. They bring multiple instruments, redundancy, high reliability, and they are able to take detailed measurements of these objects. And when we look at what we're getting, it sort of upends kind of basic spherical cow model that we were working at. And this is typical astronomy. And closer to an object, it becomes infinitely more complicated than you thought it was, and you have to completely reimagine what you're going to do about it. If you go back and look at the pre-Voyager era understanding of Jupiter, and then the pre-Galileo understanding of Jupiter, and now the pre-Juno understanding of Jupiter, every time we go and get more information, we have more questions than we had before. So we look at asteroids, and you can see these are 3 of the asteroids that we have come by. I picked all near-Earth objects. Itokawa, well, it's the biggest picture, is the smallest object. Eros and Tutatis all have some things in common. They're all oblong objects, but their surfaces, their colors, and many of their characteristics are radically different from each other. When we get to cometary nuclei, it's even worse. So here we have 4 of the comets that we have been to, one of which we actually went co-orbital with, that was 67P. And if you can find the common theme that describes all of these objects from these pictures, I would really like to talk with you afterwards, because these all, again, look very different. Again, there are some things that go between them, but all of these have a very different environment that we have to deal with when we're looking at this. So, the one-off method has destroyed the spherical cow, but it's left us with a huge number of questions that are necessary if we really want to understand these objects as a class. So we do not understand what are the surface characteristics statistically. How did it vary between these objects? The same goes for their composition, cohesion, density, uniformity. What type of rotation do they have? Is it non-principal axis? Is it principal axis? How does it evolve as a result of non-gravitational forcing or between orbits? And also, what is the operational environment we have to deal with? There's a big difference between trying to do mining at 67P and Temple 1. Very different objects. And we have to understand that if we're just going to go to an object and start looking at it, start using it. The problem is, the one-off method can't do this. What it has is a lot of capability, but it also comes with a lot of cost. The cheapest of these missions, Hayabusa 2, is somewhere around 300 million. OSIRIS-REx is $1 billion. These missions take an exceptional period of time to develop a concept, propose them, sometimes multiple times, and once they're picked, they have to be built. They're always on a dedicated launcher. There are very, very specific launch windows. So by the time you have decided you want to go somewhere and then you get there, it can be 10, 15, 20 years before it happens. These experiments can be highly customized to achieve very, very detailed scientific goals, but that also comes with a lot of cost and a lot of customization in terms of the instruments. Because of the cost, they are very risk averse. These can't fail. You can't send OSIRIS-REx and have it get all the way to Bennu and then just stop and not have that appear on the cover of the New York Times the next day. You can't have that kind of failure mode. That also increases cost and schedule and everything else. And as a result, there's a very small number of things that you can send these missions to. And as a result of that, we can't go after the phenomenological basis that makes everything work for understanding broad characteristics of these bodies. We can't do an understanding of phenomenological features, things like the compositional and dynamical classes that we've identified. If we go through all the ones that we've identified for comets and asteroids, there are more of them than there are missions that have gone to them so far. So we have yet to visit any or all of them. To this point, we've never visited an Oort cloud long-period comet. We've never been to one that was outbursting. We've never been to an object that was fragmenting. We haven't been to one, at least in a regular mission, that had satellites or rings. We've never been to a centaur, et cetera, et cetera, et cetera. So trying to cover phenomenological space is very difficult. Trying to cover statistical space. How do they rotate? What are their shapes? What are their surfaces like? These are statistical studies that if we want to use these objects as resources, we have to be able to go a long time to them. So, we're going to start right now. We're at the beginning of North American exploration. We've been to a few places, and we're extrapolating the entire continent and how we're going to use it based on Jamestown and whatever islands we visited in the 80s. It's not enough. We have 1,000 NEOs that are more than 1 kilometer in diameter, 10,000 that are more than 140 meters in diameter, 250 periodic comets, 1 to 3 long-period comets a year. We can't match to what we need to do with anything like our current model. What we need instead is a spacecraft model that involves independent operation, not daughter spacecraft, on-demand deployment, something that can go rapidly to our targets, large numbers, not just a few, tens, hundreds of objects. Low-cost data doesn't have to be fast. It can be like New Horizons, take a year to get its data back. It doesn't matter. We want low-cost data. Large delta V, so we can get to a lot of these objects. Modest reliability, understanding to lose some, and modular instrumentation that isn't so customized that it's very expensive to design. So what I'm suggesting is that we need a fleet. Not a swarm, not a daughter, a fleet. Think of it as Ford Motor Company, making the focus with different trim packages. And you buy it, you send it. And that's where Wayfarer comes in. Now, we developed this with a student program. It's purely notional, but the basic idea right now is we have a limited operating range, so we don't have to worry about thermal effects and power effects in a major way. 12U is our nominal size so that we can accommodate a few instruments. We do solar electric propulsion, Blue Canyon, because they're our partner, their attitude control system, something like 120 watts. It's not outrageous, and communication consistent with Iris, that sort of thing. We developed a very small set of instruments that we can package 2 or 3 at a time, put them on these spacecraft. This is all stuff that has been used previously at asteroid missions, and we might want to try to use again. But basically, mix and match your trim package, your XE versus limited. And the basic mission profile that we have come up with is to launch these on rideshare or individually and send them out to a parking orbit where they can be deployed on demand to any object that we want. Assembly line construction, simple, consistent flight implementations, common communication architecture, failure tolerance, and orbital storage can get us to what we want out of that. We did a little bit of orbital development in terms of taking objects from LEO and putting them in a parking orbit. Kinetics developed multiple models that can take as short as 12 days to get from LEO out to lunar L2. And from there, with a kilometer per second or so with delta V, we can get to a lot of the inner solar system. At LEO, we can put them on small rockets, low cost, large deployments, a lot of speed times, so it will work very fast. From there, any type of mission is possible. Flyby missions, become co-orbital, multiple flybys to look at different things, evolution. You can even hit it, why not? It's an assembly line, drive one focus in, drive the other focus by it. We developed orbital profiles that can get us to a bunch of Jupiter family comets, near-Earth objects, even a long-period comet, in various types of scenarios. I'll just cut to my summary here. So the point is that something like a Wayfarer class spacecraft is the sort of thing that can give us a real statistical understanding of near-Earth space. By using rideshare, low-end boosters, and orbital storage, we can reduce the cost of sending things into space and take advantage of multiple launch opportunities that reduce schedule and increase frequency. By taking an assembly line model to spacecraft, which is something we've never done before, we can have many, many more opportunities, albeit not the same quality as OSIRIS-REx, but 100 times the density of OSIRIS-REx type of opportunities. And by being failure tolerant, understanding that these are low-end technological devices that may not always handle the radiation environment, that may not always function. We build 10,000 refrigerators, 10 won't work, or 100 won't work. But being failure tolerant, we're able to reduce cost further and also be more comfortable in working in challenging environments like breakups and outbursts and other things like that. And it also can provide a technology pathfinder because Ford Focus changes its design every 3 years. And so you can upgrade as time goes by and really begin to understand the nuances of how these various systems operate by looking at them in multiple spacecraft all at the same time. And I will conclude with thanks to the students and our industry partners, and also I put this picture up here because what we immediately all thought of when we started talking about this is the class whatever probe that the Star Trek captain would send out whenever they had something that they wanted to look at. It was just fire off the probe, class 1, class 4, class 5. And boy, they must have had a ton of them. They were like Tic Tacs. So I'll stop there. Any questions?
it's a very exciting talk. My question is, this huge diversity in the bodies that you mentioned, which is very exciting from the scientific point of view, can be a nightmare for engineers, because if you want to design a modular system that has to work in very different contexts, I mean, issuing the requirements and satisfying them could be very difficult. For instance, in my institution was a PI for the sample drilling distribution system on board the FILE. And I remember that back at the time that we had to perform the tests on ground, nobody could know the density or the compressing strength of the specimen that we used, because nobody knew what we had to find there. So it was very difficult, because it would have been softer like a sponge, or harder than the marble. So I mean, how can this, I mean, on one side it's very exciting, but on the other side can be, I mean, quite difficult to handle whenever you have a modular system.
I completely agree with you that if we start, we would base the initial design on sort of what we know, and the assumption that we would not try to land, that we would stay far enough away that we could avoid some of the challenges that you're talking about right there. We would think about landing right away. And even with that said, there would be environments that we would try to go into flybys by, and say, for instance, like epoxy at Parky 2, they sent back all those great pictures of those basketball-sized chunks of ice that were floating around the nucleus. It could easily hit them, and they would never have known that happened. And that will happen if you try to do something like this. The idea is that you start with a basic design that is built on what you know. And then as you increase your statistical space, as you increase your understanding of what these environments are like, then you start to develop revision models that can do a more detailed type of investigation. But the idea is to try to get out there and explore as many objects as possible. It's not always going to work. It's not always going to be something that you can say you understand completely. Indeed, many of the objects that we're looking at right now in these pictures are things that were flown by on the way to somewhere else, or serendipitously. It's still valuable to have that information, even if it's very limited.
So I understand this was a concept presentation at this point. I was wondering what thought you'd given to the design, the forward focus that you would build for this in terms of size, and then what your parking order. I'm thinking probably a solid parking order that you can turn on when you decide the destination you want to go after. So I was wondering some little more detail.
We have done a little bit more. It was just impossible for me to put all of that in this talk. But so essentially, right now, what we're talking about is about a 12U format. We tried to cram it all into 6U, and the students came back and told me we can do it in 6U, but you only have half a U for all your instruments. And I said that will cut it. We'd like to have a couple instruments in one. So we expanded it to 12U to give us additional thrust capability and the opportunity to put in more instruments. So we've looked at existing designs for instruments like mass spectrometers and imagers and things like that. But part of the issue is that some of these are still in development, so we haven't really committed to any particular design. It was more of an identifying exactly what could go in.
About the parking orbits.
Yeah.
I understand for a comet why you want to do that, because that's basically a target of opportunity. You want to be up there when it flies by. But for the asteroids, couldn't you just go directly from any launch? There are a lot of asteroids, and electric propulsion gives you flexibility in the launch windows. So couldn't you just say, I've got a ride on August 12th, what can I get to?
You could definitely do that, yes. Part of the idea is that by having a lot of them sort of ready to go, you can identify I want to go to these objects I have launched now, I can park them, and then when they come by later, we'll pick them up. You can also have them as a resource. You can imagine that you say, okay, NASA has a proposal opportunity where they say we have 10 Wayfarers, where would you go? Write a proposal, something like that. But you're absolutely right. You could also just get on a flight and go directly there. In fact, well, I don't really need to go back to it, but we developed that very model as our first one. The first model we designed was, let's suppose that we could put a Wayfarer in geostationary orbit with a camera and a mass spectrometer and fly it to Comet 73P Schwarzmann-Lachmann 3 in its 2022 apparition, which we could predict. And we had it spiral out of geostationary, head out to Schwarzmann-Lachmann 3, have an encounter with Schwarzmann-Lachmann 3, and then actually come all the way back to Earth and reinsert itself into the L2 for 4.2 kilometers per second delta V. So yes, you could do it that way too.
You briefly mentioned about creating a fleet. So in that case, are you building these Cubesats from scratch? Are you buying components from elsewhere and integrating them? So if it's the latter, then what is sort of the gap in the market which you would like to be filled? So something which the community, not industry, is addressing what the industry would address.
Well, I think initially the idea is that we would use things that people have already built, where the potential for economy of scale is the greatest. And then when I say assembly line, I really mean that. We talked a little bit with Raytheon Missile Systems, which is headquartered in Tucson, when we were beginning to think about this. And they said, yeah, this is about the level we've become interested in. And in fact, we can't tell you without killing you about this beyond the number, but we just finished building 300 CubeSats for an unnamed organization. So they're ready. They are already thinking about doing this sort of thing, assembly line stuff.
Yeah, related to that, how cheap can you make them? Is it really a Ford Focus?
I don't know yet. I mean, all I can tell you is that the best example I can come up with was in the year 2000, if you wanted a 24-inch plasma TV, it would have cost you $40,000. Now you could get a 70-inch 4K LCD TV for $1,500, at least at Costco. And almost all of that is economy of scale. So I'm hopeful that we can really drive the cost down.
Can I make a suggestion? One of the projects I've been looking at recently that's been put together, hopefully at JSC, is an on-orbit assembly system for delivering satellites. What I've seen ostensibly is a 48-3U system with a solar electric propulsion running out of ISS, going out to wherever you want to go, dropping off your payloads and coming back and being replenished and ready to go again. And I'm just wondering, is that some kind of thing that might be of interest to you?
Oh, absolutely. In fact, there's only so many things I can present here, but one of the things that we talked about was, well, you could always pick 20 of these things and put them on an Esper wing or something like this and have that take them out. And then they take all of that delta V with them, and that increases the number of things that they can get co-orbital with, or their operational range. So yeah, any type of rideshare to that parking orbit would be something I'd be interested in seeing.
Typically, the CubeSat has a very short lifetime. Is it possible to stay on the parking orbit for a very long time? From my experience, the Earth-Moon liberation point orbit, the spacecraft may undergo a very long eclipse. It's also very difficult for the surviving at such a long eclipse period. I think maybe the Sun-Earth liberation orbit is better than Earth-Moon liberation orbit.
It might be. I mean, the Earth-Moon is the one that we developed. we would have to look at various options. This was the one that we thought was easiest to get to from an orbital perspective, especially for you're also correct that exposure to solar wind and other environmental factors, we don't know how long current technologies can survive in those environments because we have very little data. We have less data about Cubesat subsystems than we do about small bodies from one-off missions, to be honest. The analogy that we went with for this was the Sojourner analogy, which is, Sojourner was with Mars Pathfinder, and they used to joke that they bought all the components at Radio Shack, and that worked really well for an extended period of time. Or you can think of Spirit and Opportunity, how long they operated despite the fact that none of the equipment was made for them. That's where the failure tolerance has to come into play. If you launch 20 of these and the environment kills 3, so what? That's kind of the way that we were approaching this, is that you're still going to get 17 missions for very low cost by comparison with going there with Osiris-Rex. So,
Thank you. Okay, maybe time for one more. Is it quick like that? All right, we'll move on. Thanks very much.
okay.
Yeah, all right.
Last question. Very quick one. So I was just hoping you could elaborate a bit more about the ground operations. So it's all well and good having 24 focuses in space, but tracking all 24 focuses in space must be quite expensive. So are you doing them one at a time and then tracking one, and then once it's completed, you just sort of writing it off and then doing the next one, or just hoping you could explain a bit more about that?
Well, that's a very good point. Once you get to a large number of these things, communication strategies get harder and harder. We sort of base this communication strategy and ground support operations off of the model that was developed in Arizona for Osiris-Rex, scaling things down so that we can do it at sort of the student level with a small dish. The more of these things you have, the more dishes you need, the more ground support staff you need. So there is a scaling factor that has to come on. But the idea is to develop whatever scheme we use to be low enough in cost and complexity and transferable as a sort of package from place to place to place that we can replicate it, just like we're replicating the spacecraft themselves. So that not everybody is coming up with their own ground support system from scratch. Kind of buy it off the shelf.
Thanks very much. Let's thank our speaker again.